Burbank, California, March 1960, 2:47 a.m. A Lockheed engineer stands on the factory floor staring at a pool of expensive jet fuel spreading beneath a gleaming titanium aircraft. His clipboard trembles slightly. The CIA's most classified project is hemorrhaging fuel like a sieve, and tomorrow morning the director himself is flying in for inspection. But here's what nobody expected. The engineer smiled, picked up a phone, and told his supervisor, "It's working exactly as designed." How could a fuel leak be intentional? Why would brilliant engineers at Lockheed's Skunk Works deliberately create an aircraft that dripped thousands of dollars worth of specialized fuel onto the tarmac every single time it sat still? And what does this tell us about solving impossible engineering problems when the laws of physics seem to be working against you? Today, you're going to discover how titanium panels designed to expand several inches at Mach 3 solved one of the most counterintuitive challenges in aviation history. This is the story of the SR-71 Blackbird's leaking fuel system and why sometimes the best engineering solution is to embrace the problem instead of fighting it.
Let's go back to 1958. The Cold War is at its peak. The CIA has a problem. Their U-2 spy plane, which had seemed untouchable just 3 years earlier, is now vulnerable. Soviet radar technology is improving fast, and American intelligence analysts know it's only a matter of time before a U-2 gets shot down. They need a replacement. But not just any replacement. They need an aircraft that can fly higher, faster, and be virtually invisible to enemy radar. The specifications sound impossible. Mach 3 plus cruise speed, operational altitude above 80,000 feet, range of 3,000 nautical miles, and a radar cross-section small enough to confuse Soviet systems. The CIA approaches Clarence Kelly Johnson, the legendary chief engineer at Lockheed's Advanced Development Projects Division, better known as Skunk Works. Johnson had already given them the U-2. Now they needed something that would make the U-2 look slow. Johnson accepts the challenge, but there's a catch that nobody fully understands yet. To fly at Mach 3, the aircraft will experience something no production airplane had ever faced: extreme aerodynamic heating. When air molecules slam into the aircraft's surface at 3 times the speed of sound, friction generates temperatures that would melt conventional aluminum airframes like butter. The leading edges of the wings would reach 1,100 degrees Fahrenheit. The nose cone would hit 1,050 degrees. Even average skin temperatures across the fuselage would hover between 450 and 600 degrees Fahrenheit. For comparison, that's hot enough to bake a pizza. Aluminum, the standard material for aircraft construction in 1958, starts losing its structural strength at just 350 degrees Fahrenheit. Steel is too heavy. There's only one material that can survive these temperatures while remaining light enough for sustained high-altitude flight: titanium. But here's where the story gets interesting, because choosing titanium solved one problem and created a dozen others that nobody had anticipated.
Titanium in 1960 was not the common aerospace material it is today. It was rare, expensive, and incredibly difficult to work with. Lockheed's Skunk Works team had to invent entirely new manufacturing processes just to shape the metal. But Kelly Johnson faced an even stranger problem. The world's largest supplier of titanium in 1960 was the Soviet Union. The very country they were building this spy plane to monitor controlled most of the global titanium supply. Johnson's solution was as audacious as the aircraft itself. The CIA created a network of shell companies that purchased titanium from Soviet sources, with the Russians believing the metal was destined for pizza ovens and other commercial applications. The irony was perfect. Soviet titanium would form the skeleton of the aircraft designed to spy on Soviet territory. By 1962, Lockheed had secured enough titanium to begin construction. The SR-71's airframe would be 93% titanium by weight, with some steel and composite materials filling out the remaining structure. But as engineers began fabricating the first panels, they discovered titanium's dark secret. The metal expands when heated, not just a little, a lot. Physics tells us that titanium has a coefficient of thermal expansion of approximately 8.6 parts per million per degree Celsius. That sounds small until you do the math on an aircraft that's 107 feet long, experiencing temperature increases of more than 500 degrees Fahrenheit. The SR-71's fuselage would grow more than 4 inches from nose to tail during a high-speed cruise. The wingspan would expand. Panel edges would shift. Every rivet, every seam, every joint would be subjected to forces that could tear a conventional aircraft apart. And then there were the fuel tanks. The SR-71 needed to carry 80,000 pounds of fuel for its long-range missions. But unlike conventional aircraft with separate fuel bladders, the SR-71's fuel tanks were integral to the structure itself. The wings weren't just wings, they were also fuel tanks. The fuselage sections weren't just structural elements, they held fuel too. This meant engineers had to create a structure that could flex and expand with temperature changes while somehow keeping 12,000 gallons of specialized jet fuel from leaking out. It was a problem that seemed to have no solution. Seal the tanks too tightly, and thermal expansion would crack the seals or buckle the panels. Make the structure too flexible, and it wouldn't have the strength to handle supersonic flight loads. Kelly Johnson's team spent months testing different sealing compounds, different panel designs, and different structural approaches. Every solution created new problems. Flexible seals couldn't handle the temperature extremes. Rigid seals cracked under expansion stress. Complex mechanisms added weight and potential failure points. The breakthrough came when an engineer asked a radical question. What if we stopped trying to prevent the leaks?
The solution Kelly Johnson's team developed was brilliant in its simplicity, even though it seemed completely backward to everyone who first heard it. They would design the SR-71 to leak fuel while sitting on the ground, deliberately, intentionally. Here's how it worked. The titanium panels that form the fuselage and wing surfaces were fitted loosely during construction. Gaps of up to 1/8 inch were left between panels. The fuel tanks were sealed with a special polymer sealant that remained flexible at room temperature, but these seals were designed to accommodate the gaps rather than eliminate them. On the ground, with the aircraft cold, these gaps would allow fuel to seep through joints and panel edges. Puddles of JP-7 jet fuel would form beneath the aircraft. Ground crews became accustomed to seeing fuel dripping from the Blackbird before every flight. It looked like a massive design flaw. But once the SR-71 took off and accelerated to cruise speed, everything changed. As the aircraft climbed to altitude and pushed past Mach 3, aerodynamic friction heated the titanium skin. The metal began to expand. Those loose-fitting panels that had been separated by gaps on the ground now pressed tightly together. The expansion essentially created a thermal seal. At cruise temperature, with the fuselage stretched to its maximum length and the wing panels expanded to their operational dimensions, the gaps disappeared. The seals compressed into perfect sealing surfaces. The fuel tanks became virtually leak-proof at the exact moment they needed to be, 80,000 feet above enemy territory, traveling at 2,200 miles per hour. But the engineering didn't stop there. The team had to address another critical issue, the corrugated skin design. If you've ever seen photographs of the SR-71 up close, you might have noticed that sections of the skin appear wrinkled or corrugated rather than smooth. This wasn't a manufacturing defect, it was genius. A smooth titanium skin would expand uniformly when heated, but the expansion forces would have nowhere to go. The result would be catastrophic buckling, warping, or even splitting of the metal. The corrugated design allowed the skin to expand both vertically and horizontally. The corrugations could flex and accommodate the expansion forces without compromising structural integrity. Think of it like an accordion. When you pull an accordion apart, the folded sections expand outward. When the SR-71 heated up,
Its corrugated panels worked the same way, absorbing the expansion forces that would have destroyed a smooth surface. The wing design incorporated similar principles. The wings acted as integral fuel tanks, meaning the fuel was held between the wing's skin panels and internal structure. Engineers used beaded and corrugated external surfaces on both upper and lower wing panels. As temperatures increased during flight, these surfaces could expand and contract without creating stress concentrations that might cause cracks or failures. The entire aircraft was essentially designed to be larger in flight than on the ground. Every dimension, every clearance, every structural interface was calculated for optimal fit at cruise conditions, not at rest. This meant accepting that the aircraft would be imperfect while parked and perfect while performing its mission. But thermal expansion created challenges beyond just fuel leaks. The landing gear had to be designed with expansion in mind. Wheels and tires were housed in insulated buckets within the main gear wells to protect them from the intense heat that would radiate through the structure during cruise. Door mechanisms included expansion joints that could accommodate the changing dimensions. Even the engines had to account for thermal growth. The Pratt & Whitney J58 engines were mounted in nacelles that could expand independently from the wing structure. The interface between engine and airframe included flexible connections that could handle differential expansion rates. The canopy presented its own puzzle. The pilot's windscreen had to remain clear and structurally sound while temperatures on the outer glass surface reached 600 degrees Fahrenheit. Engineers solved this with a three-layered design: an outer monolithic glass panel, an air gap, and an inner laminated glass assembly. The air gap acted as insulation, while heated air circulated through the space to prevent fogging and ice formation. Flight controls added another layer of complexity. The elevons, combined elevator and aileron surfaces on the wing, had to maintain precise aerodynamic control while the wing structure around them expanded and contracted. Hydraulic actuators were designed with thermal compensation to maintain control authority across the entire temperature range.
So what was it actually like to fly an aircraft designed to leak fuel? Former SR-71 pilots have shared fascinating insights into the operational reality of this counterintuitive system. Before every flight, ground crews would fuel the SR-71 with approximately 65,000 pounds of JP-7, a special low-volatility jet fuel developed specifically for high-temperature operations. JP-7 had a flash point of 140 degrees Fahrenheit, meaning you could literally throw a lit match into a puddle of it without igniting the fuel. This safety characteristic was essential given the fuel leak situation. As the fuel went into the tanks, it would almost immediately begin seeping out through the panel gaps. Maintenance crews placed drip pans under the aircraft, but even these couldn't catch all the fuel. The concrete beneath SR-71 parking spots often showed dark stains from years of fuel drips. Pilots would conduct their pre-flight walk-around inspections while stepping over puddles of JP-7. The sight of fuel actively dripping from their aircraft required a complete mental adjustment. Every instinct of a trained pilot says a fuel leak is an emergency. In the SR-71, it was Tuesday. After engine start, the leaking would sometimes increase temporarily due to vibration and fuel pump pressure. The aircraft would literally leave a trail of fuel drops as it taxied to the runway. Ground crews had to be careful about ignition sources, though the low volatility of JP-7 provided a significant safety margin. Once airborne, the mission profile was carefully choreographed around the thermal expansion timeline. Most SR-71 missions required an immediate post-takeoff refueling from a KC-135Q tanker aircraft. Contrary to popular belief, this wasn't primarily because of fuel lost through leaks. The aircraft was deliberately fueled to only 65,000 pounds for takeoff to reduce weight and improve performance. The full 80,000-pound fuel load would be added during aerial refueling once the aircraft was aloft and burning fuel rapidly during its climb to altitude. As the SR-71 climbed and accelerated, pilots could monitor temperature gauges that showed skin temperatures across different sections of the aircraft.
The nose would heat up first, followed by the wing leading edges. Within 15 to 20 minutes of reaching cruise speed and altitude, the entire aircraft had thermally stabilized at its expanded dimensions. At this point, the fuel leaks stopped. The integral fuel tanks, now sealed by thermal expansion, held their contents perfectly. The fuel itself served multiple purposes during cruise. It was not just propellant for the engines, but also a heat sink. JP-7 was circulated through heat exchangers to cool avionics equipment, hydraulic fluid, and even the engine oil. By the time the fuel reached the engine combustors, it had absorbed enormous amounts of waste heat from aircraft systems. But what happened when the mission was over? As the SR-71 descended and decelerated, the cooling process reversed the expansion. Pilots would sometimes hear pinging and popping sounds as the titanium contracted. The panels would pull apart slightly, the seals would develop gaps again. And yes, the leaking would return. After landing, ground crews would service the aircraft while fuel dripped on the ramp. The cycle would repeat for the next mission. Some pilots joked that the SR-71 wasn't really parked, it was just temporarily between puddles. The fuel leak design actually had an unexpected benefit. It served as a diagnostic tool. Maintenance crews became expert at identifying abnormal leak patterns. If fuel was dripping from an unusual location or in greater quantities than expected, it might indicate a damaged panel, a compromised seal, or structural fatigue that required attention. The normal leak pattern was actually reassuring because it meant the expansion gaps were properly sized. Over the SR-71's operational lifetime from 1964 to 1999, the intentional leak design proved remarkably reliable. The aircraft completed thousands of missions with virtually no fuel system failures attributable to thermal expansion issues. The solution that had seemed so counterintuitive became one of the program's greatest engineering successes.
The SR-71's thermal expansion approach influenced aerospace engineering in ways that extend far beyond reconnaissance aircraft. The lessons learned from deliberately designing for operational conditions rather than ground conditions shaped thinking about spacecraft, supersonic transports, and hypersonic vehicles. NASA's Space Shuttle, for example, incorporated similar principles. The thermal protection tiles that covered the shuttle's surface were designed with expansion gaps filled with flexible material. The designers understood that trying to create a perfectly sealed surface would result in tile damage or detachment during the intense heating of re-entry. Modern supersonic aircraft projects, including concepts for next-generation reconnaissance platforms and commercial supersonic jets, continue to grapple with thermal expansion challenges. The SR-71 solutions remain relevant. Corrugated skins, expansion joints, and structures designed for optimal fit at operating temperature rather than ground conditions. The titanium manufacturing techniques developed for the Blackbird program also had lasting impact. Lockheed's Skunk works pioneered methods for working with titanium alloys that became industry standards. Today, titanium is commonplace in aerospace applications, but in 1960, almost everything about shaping, welding, and assembling titanium had to be invented from scratch for the SR-71 program. Interestingly, the fuel leak characteristic became one of the SR-71's most famous features. It's mentioned in virtually every documentary, article, and book about the aircraft. The image of the world's fastest jet dripping fuel on the ground became iconic, a perfect illustration of how engineering solutions can defy common sense while remaining absolutely correct. The program also demonstrated the value of accepting unconventional solutions. Kelly Johnson and his team could have spent years trying to develop seals and structures that would prevent leaks under all conditions. Instead, they recognized that the operational requirement was to contain fuel during the mission, not on the ground. By reframing the problem, they found a solution that was simpler, lighter, and more reliable than any alternative.
Today, as aerospace engineers work on vehicles capable of even higher speeds, the SR-71's lessons remain critical. Hypersonic aircraft operating at Mach 5 or beyond face thermal challenges that make the Blackbird's problems look modest. Material science has advanced, but the fundamental physics of thermal expansion hasn't changed. The SR-71's approach embrace the problem, design for operational conditions, and accept imperfection at rest in exchange for perfection in flight, remains a masterclass in engineering philosophy. Sometimes the best solution isn't to eliminate a problem, but to manage it intelligently. The leaking fuel system stands as a testament to innovative thinking. It reminds us that the most effective solutions often come from asking different questions rather than trying harder to answer the original ones. Instead of, "How do we stop the leaks?" Kelly Johnson's team asked, "When do we actually need to stop the leaks?" That subtle shift in perspective made all the difference. 32 SR-71 aircraft were built. 12 were lost to accidents over the decades, but none of those losses were attributed to fuel system failures caused by thermal expansion. The intentional leak design worked flawlessly for 35 years of operational service. That's a remarkable engineering success by any measure. If you found this deep dive into engineering problem-solving fascinating, make sure you're subscribed to this channel. We focus on the technical innovations and clever solutions that changed military history, from communication breakthroughs to engineering marvels like this one. Next time, we're going to explore how engineers built a 500-foot bridge in just one night during World War II, a construction feat that sounds impossible until you understand the ingenious Bailey Bridge system. And if you want to dive deeper into Cold War aviation technology, check out our video on how the U-2 spy plane's design created its own set of impossible engineering challenges. That link is in the description. The SR-71 Blackbird, an aircraft designed to leak fuel expanding several inches during flight, made from Soviet titanium and fueled by a substance that wouldn't ignite if you dropped a match in it. Sometimes the best engineering is the kind that makes perfect sense once you understand why nothing else would work.